Hello and good morning. Thank you all for having me. My name's Joe Walker. I'm a postdoc at the Scripps Institution of Oceanography. My co-authors are Aaron Deans, Lauren Baggett, Sean Wiggins, and Caitlin Frazier. We're all researchers, students in the machine listening lab at the Scripps Institution of Oceanography. And so today I'm going to be presenting to you guys our work that we've titled Listening on the Edge, Real-Time Multi-Target Acoustic Tracking for Mobile Assets. And so I want to start by kind of explaining to you guys like why we at Scripps we're interested in this problem of multi-target tracking. We primarily focus on like ecology and that sort of thing. So I'm going to start by kind of, motivating the problem a little bit from our perspective. And so in our lab, we're primarily interested in understanding the distribution, abundance, and movements of marine mammals using passive acoustic monitoring, where we basically listen for and detect the echolocation clicks that these marine mammals use to navigate and forage. And our primary tool for doing this is with seafloor mounted hydrophone arrays. And so basically, as you can see in this illustration, we basically moor these hydrophones to the bottom of our study site. And we basically just listen for anything that may come across our sampling volume. And so this has a couple problems. One, there's limited operational awareness. Basically, what I mean by that is once we put this thing at the bottom of the ocean, we have no idea if something breaks, if something goes wrong. We basically only realize that once we retrieve the system and look at it. And also, it only allows for static monitoring. If we can't like move with or pursue some interesting source that we might detect. And I also want to say that, so this presentation is primarily motivated by studying marine mammals and tracking marine mammals, but you can use your imagination and think about what other things you could be tracking in the wild. And so with these limitations in mind, there's growing interest in our lab to consider autonomous vehicles such as wave gliders. And in this illustration here, I show what a wave glider system looks like. Usually you have a surface component, which might have solar panels, a GPS receiver, maybe a radio antenna. And at the bottom, it has this basically it's kind of like an airfoil where it uses wave energy to propel itself, and it can tow a hydrophone array. And so this has the advantage of allowing for continuous operational awareness, right? We can communicate with this surface component, and it allows for dynamic monitoring, and it can actually move. But to actually receive the benefits of dynamic monitoring with the mobility, you don't want to just move around aimlessly in the environment, right? You want to have some sort of intelligent way of detecting something and moving with it. And so for that reason, if we wanted to maintain some optimal distance with something that we've detected, there's a need to equip the system with real-time processing capabilities. And so that's what I'll be presenting to you guys today, all the work we've done with developing a real-time multi-target tracking system. And there may be more accurate, more powerful systems out there using maybe reinforcement learning, but here we're specifically finding a solution for a low power system, like think of like a Raspberry Pi or even a microcontroller. And so the algorithm is going to be kind of informed by our hardware platform and our setup, right? And so far in our lab, we've developed a tow body system that's equipped with the following components. We have hydrophones that are arranged around the outside of the tow body. We have a data logger, which is basically sampling the analog signal coming from the hydrophones and saving it to persistent storage. We have battery pack, and then we have a Raspberry Pi, which is basically taking data from the data logger and doing this real-time processing. So right now, all of the work we've been doing with real-time processing is taking place on a Raspberry Pi 02W. And so, okay, so before I go into the details of our tracking algorithm, I kind of want to back up and talk about how do you even determine the direction of a source underwater, right? Like what's kind of the elementary signal processing steps. And so before we can track, the steps are we first need to calculate TDOAs, which are time difference of arrivals. And then we convert those time difference of arrivals to a direction of arrival, which is basically just a three-dimensional unit vector pointing to the direction of the source. And so It starts by our whale or your whatever. It makes a sound, and that pressure wave will propagate towards your hydrophone array, and it'll arrive at different times, right? Slightly offset. So it might arrive at the red hydrophone first, then the blue one, then the orange one, and then the green one. And so the next step here is to calculate the time difference of arrivals between the sensors. And so to do this, we use this algorithm called the generalized cross-correlation phase transform algorithm. Basically, it's a frequency domain implementation of cross-correlations, right? So we consider a time window. In our application, we consider 10 milliseconds. And we apply this GCC fat algorithm to each unique pair of hydrophones. And so the output of this GCC fat algorithm is this offset delta function in time domain, and that offset gives you that time difference. This will be the most amount of math I show in this presentation, I promise. And so we've computed these TDOAs, right? And so what we know at this point is our TDOA vector. We make a guess or an estimate for sound speed. This is kind of one of our things on our to-do list of how to better come up with an estimation for sound speed. And so we also know our matrix of relative hydrophone positions. Our hydrophones are oriented around the tow body, and so while that might be rotating, it's rotating as a rigid body, so the relative positions are fixed. And so and then U is our sound direction, our direction of arrival vector that we want to solve for. And this basically boils down to a simple linear algebra problem. Use linear least squares with singular value decomposition to calculate a pseudo inverse. And it's, yeah, very simple and computationally efficient. And so at this point, I want to emphasize that our tracking algorithm, we are tracking in the direction of arrival domain. So we're basically tracking the direction at which these sources are emitting sound from. We're not tracking absolute position, but if you had multiple wave gliders or multiple systems and they could communicate, you can imagine you could cross these vectors and get absolute position if you wanted to. But right now I'm showing what we've done with just tracking the direction. Okay. So yeah, that explains how we calculate direction. And so basically our algorithm starts by considering a window of time where we aggregate all the DOAs in which we've calculated and we cluster them together. And so we use clustering, specifically the DB scan algorithm, to estimate the number of sources. And so in this illustration here, this isn't like real data, but it's an illustration I created to kind of resemble what it actually does look like when we cluster. And so I've drawn here these 3 clusters in the orange, green, and red. And the reason I've drawn them as like these kind of irregular, elongated shapes is because in that time window in which you're clustering, their target could be moving. So that's why it's important to use a clustering algorithm like DB-scan to identify these clusters. It's very good at picking out these kind of really wonky shaped clusters. And because these points are actually time-stamped, not only can we estimate the number of targets, but if you can see the X's I've drawn at kind of the darkest points in the cluster, we know the most recent position, the most recent data point that falls within each cluster. So the clustering step, in summary, we estimate the number of targets and their most recent position. And so the next step is, okay. So the next step is using the most recent position. We use that direction. We use that to initialize a Kalman filter. And this Kalman filter is what's going to be responsible for basically tracking the movement of these targets. And so we initialize our Kalman filters. And so then for each new DOA observation that we obtain, we associate that observation with no more than one of the existing Kalman filters if it falls inside of some noise perimeter that we define for the Kalman filter. If it falls outside of it, then we disregard it as noise. But if it falls inside of the noise perimeter, we update the state of the Kalman filter. And so because targets can appear or reappear, the simple solution we found for this is to basically define a clustering frequency in which we repeat the clustering process. So in summary, we might for every 60 seconds, we will cluster the last 30 seconds worth of data to kind of update the number of targets that we wish to track. And so then, there's a process of, for all the new targets, for all the new clusters that you find, you have to either associate it with an existing Kalman filter that already existed, or initialize a new Kalman filter. Or if you have some Kalman filter that hasn't been associated with a new cluster for a few clustering iterations, maybe that means that that target has gone out of range, stopped producing sound, and you need to destroy that Kalman filter to kind of prevent these dangling Kalman filters from just accumulating. And so now I'm going to show you guys some results of the algorithm, but I just want to first say that these results were obtained under simulated real-time conditions. We haven't actually put this tracking algorithm in a waveglider setup yet, but we have data that has been collected in that context. And so basically what we do is we take that data, push it through this simulator program, which basically, chunks the data into UDP packets and sends it to our Raspberry Pi to simulate a real-time environment using real data. And so we then record the DOAs. To make it easy to visualize, we encode the DOAs using an azimuth and elevation, right? If you think of like a direction of arrival, I can encode that direction as some azimuth, some azimuth angle and then an elevation. And so here's the first track example where you're looking at the raw recorded DOAs. And so it's a pretty challenging example. I'm going to be showing you guys like kind of the most difficult tracks that we tend to encounter. Usually there's either long periods of nothing vocalizing, but then other times there's maybe just one or two things. But so in this example, there appears to be like 3 targets, if you kind of see, and they're detected intermittently. They're kind of like vocalizing, then going quiet, vocalizing, then going quiet. And then there's also a high degree of noise. But if you look at the results of our tracking algorithm, you can see it does a pretty good job of picking up the 3 sources, even when there's a high degree of noise and vocalizing inconsistently. And I also want to say at this point that we don't have any kind of quantitative way of judging the performance of the tracker. We basically just kind of look at the DOAs on the left and then look at the results and ask ourselves like, are we happy with it? Is it performing well? That's kind of what we're doing. And so now I'm going to show you a really hard example. And so this is probably the hardest instance of whale tracks that I've come across. And so basically what makes this hard is we're considering a longer period of time, and they're kind of vocalizing intermittently. In the beginning they vocalize and then they stop. But they also tend to be swimming in this almost like double helix kind of structure, almost like they're trying to evade our tracking algorithm. And then there's also like some noise at the end. And so this was tricky because in this instance, our algorithm initialized 10 Kalman filters, not meaning it was tracking 10 things at once, just in the total of this time, it initialized a total of 10 different Kalman filters. And so what the issue is here is that in the beginning, it tracks something, and then 10 minutes goes by, so it's killed off that Kalman filter and has to create a new one to pick it back up again. But still, I mean, the main kind of patterns in the track look decent. And so then this is the last example I've shown here. Looks like we've picked, the algorithm has picked up 5 different sources, probably another issue of intermittent vocalizing. And I also want to add that this is the track in which we kind of learned or tuned the parameters of the tracking algorithm on. So I talked about like a clustering frequency, a clustering window, a noise parameter. How do we estimate those values? I did that using data from this track, and the performance of these 2 tracks are just out the box performance. No tuning, nothing whatsoever, just press go. Okay, so, and at this point, I want to talk about a potential performance optimization, which we're having some success with. And so what we do is we have all these steps of like calculating TDOAs, then DOAs, and then clustering, and then ultimately we do all the signal processing, and 80% of the points get thrown away as noise samples, right? And so ideally we would have some sort of way of removing these samples that correspond to noise at an earlier stage in the processing. And so for this reason, we want to see if we can use a neural network and kind of use it as like a kind of smart filter to just do something very simple, like distinguish between kind of biological signal or non-biological signal. And so I'm not going to go into the details. If you want to know more, I can ask during the questions, but we train a model, perform quantization to make it small, like convert it from 32-bit floating point to 8-bit integers. And then we get a model that we can ultimately run on the Raspberry Pi in just half a millisecond. And so here I'm showing you, on the left is the original track, and on the right, that's when we're actually using the neural network to filter out the noise. It does a pretty good job of filtering out the noise while preserving the kind of main body of the track. But there are some issues though. You can see those instances in the very beginning where the mammal was vocalizing. We kind of lost it. So because the neural network doesn't have perfect recall. So kind of something we're still working on. And so I'm running out of time here, but I want to talk about the power consumption. While the neural network helps reduce the program power consumption by about 23%, the overwhelming majority of the power consumption is coming from just the Raspberry Pi's baseline power draw. So it's hardly an optimization at all on the Raspberry Pi. So this is really frustrating. And for this reason, our future work, well, really our current work, is moving away from a Raspberry Pi to a microcontroller. And we also want to improve the classifier, add some more classes, maybe distinguish between like ship noise and flow noise or different biological signals. So I'm gonna wrap it up here. And so thank you guys. Those are my contact information. We're hopefully going to have a paper out by the end of the year, and we want to make the code open source when we do have that paper out. And yeah, our funding is this right there. I'm funded by the Schmidt AI and Sciences, and thank you very much.